Okay, so theorem 1.11, properties of continuity. Okay, all it says is if B is a real number and F and G are continuous at C, then the following functions are also continuous. All it's saying is if F and G are both continuous, then when I do the math, it's what? Continuous. That's it. Okay, so number one says if I multiply by a scalar, it's still continuous. If I add them or subtract them, they're still what? Continuous. If I multiply them, they're still what? Continuous. When I divide them, they're still continuous. If they were continuous over the interval to begin with, when I do the math with them, they're still going to be what? Continuous. That's the statement you need to say about that. That's what 1.11 says. If they were continuous on an interval to begin with, after you do any math, are they still going to be continuous? Yes. So don't write all that, just that statement. Which kind of is one of those duh things, but we got to say it.
What was it again?
If the two functions were continuous over the interval, before you did the math, they will be continuous after you do the math.
But we don't need to write like 1, 2, 3.
No, I don't think you do. Do you?
Oh, no, it's not.
It just multiply by scalar, add, subtract, multiply, divide. You know what those mean.
I've never heard of scalar multiple.
Yes, you have. We did scalar multiplication with matrices. Scalar multiplication is just making everything 3 times bigger or half smaller. It's just multiplying it by one constant. Okay, the next one is just another thing. I don't think you really need to think about this. You need to just, I don't think this needs to be written down. I think you need to think about this. Just think about it, okay? The first one says the following types of functions are continuous at every point of its domain. A polynomial. There is not one fraction in this polynomial with a variable in the denominator. So is the domain all real numbers?
Yes.
Yes. Is it continuous? Yes. Okay, we know that already. Okay? We know that a rational number, the rational equations that we did were continuous except when we had what?
0 on the bottom.
0 on the bottom. Except at an asymptote.
Didn't we have to factor it out?
Yep, but it's going to be discontinuous whatever makes it 0, right?
So if there's ever an X on the bottom.
Whatever makes it 0, it is discontinuous at that point, whether it's a removable or a non-removable. But that's the only point that it's discontinuous.
So like if it's x minus 9, it can't be 9.
Oh, yeah.
Yeah. Okay, so a radical is continuous over its entire domain. Is a radical like square root? That function is only from 0 to positive infinity for my domain, correct? Mm-hmm. So any even root, it is continuous from 0 to positive infinity. Odd root, it's continuous over the whole number line. So again, they're continuous over that function's domain. That's all they're saying here. Okay? Then we have trigonometric functions, sine, cosine, tangent, cotangent, cosecant, all those. They are continuous over their domains. What is ever in the domain, they are continuous over that. There are many other, and it also says there are many other functions, but these are the ones we use. Are most functions continuous over their domain?
Yeah.
Yes, until you start throwing in application problems on it. That's all this is saying. Okay? So just something we needed to discuss, not really write down. Okay, intermediate value theorem. This is something, what it says, if f is continuous on a closed interval, a to b, if f of a does not equal f of b, and k is any number between f and b. Okay, so here's f of a, here's f of b, looking at my picture. Let me point it out so if you're watching at home you can see. F of a, f of b. Everyone see that? Mm-hmm. K is some value that falls in between f of a and f of b. So f of a and f of b. Then there exists one number c over the interval ab such that f equals k. F of c equals k. It's just saying if it is continuous here, is there going to be a value at least one time it's going to hit? Yes.
So I shouldn't write anything down.
Okay. Just know that the intermediate value theorem says if there is one thing on one side and one on the other, there has to be a 0 in between. There has to be something in between if it's continuous. okay? Now, if I had something like here, look at the second one, okay? F is not continuous over AB, is it?
No.
We've got a gap. So does there have to be a point that I hit?
No.
No. But on the first one, is it continuous over A to B? So does there have to be at least one value in there? Yes. Another thing the intermittent value theorem comes into is right over here. Okay? If I am positive on this side, on the left, and negative on the right, what has to be in the middle there somewhere? What has to be there? What is this arrow pointing at?
A value.
What value? What specific value is that?
0.
A 0 at an x-intercept, correct? If you have an A to a B and A is positive and B is negative, does there have to be a 0 somewhere in between there? Yes. If B is negative, if B is negative and A is positive, there has to be a 0 in there, doesn't there? Okay? So the intermittent value theorem, that is what it's mostly used for. When you change signs, does there have to be a 0 somewhere in between?
Yes.
Yes. If it is continuous. If it is not continuous, does there have to be?
No.
No.
So there has to be, if it's continuous, on K or
In between the interval A to B.
Okay.
Okay, if it's continuous over the interval A to B. So like A to B is on the x-axis, but f of A and f of B, those are y values. Those are just the points that I plug in. So if it's continuous, it has to hit the graph somewhere. Yes? That's all it's saying. And you need to know that, that's what it is. Okay, that's weird that it's in the middle of the page. Huh. Use the intermittent value theorem to show that the polynomial function x cubed plus 2x minus 1 has a 0 over the interval 0 to 1. Okay? So if it has a 0, one needs to be what? Positive, and one needs to be what? Negative. Okay? So I'm going to say, and this is interval inclusive, yes, because they have brackets. Everyone following?
Yes.
So I'm going to take f of 0, and that's going to be 0 plus 0 minus 1, so I get negative 1.
Yep.
Okay? And then I'm going to take the other, f of 1, gives me 1 plus 2 minus 1, which gives me positive 2. Okay, since 1 is positive and 1 is negative, does this graph have to cross the x-axis? So this graph at 0 is somewhere up here, yes?
Where?
Somewhere up there. What's that? Negative 1, actually. Sorry. Negative 1. I was going the wrong direction, wasn't I? And at 1 is what? 2. And this is a polynomial function, and polynomial functions are continuous, yes? Yeah. And so does this graph have to cross here?
Yes.
It has to cross. We proved there was a 0. Did we say where it was at? No. Okay. This tells me there is a 0, but does it tell me where it's at? No.
And it tells us it's a 0 because we got negative 1 and 2.
We got a negative and a positive.
Yeah.
Not even, I don't care if it's a negative
Right.
1 or a positive.
negative and a positive.
Just a negative and a positive. If we would have got a positive and a negative, does it tell me there has to be a 0 in there? So again, the intermittent value theorem tells you it's there, but does it tell you what it is?
No.
No. We have to do some other things to figure out what it is. We would have to factor it or do long division, or actually you're going to find the zeros of the first derivative, but you don't know that yet. So there's the intermittent value theorem tells us it's there. We're going to learn methods to find out where it's at. Okay? So today when it says use it to show there is, then you better get one positive, one negative, right?
So is that one down there negative 1?
Yes.
Negative 1, 0, so
That's right here. Right here.
uh-huh.
And then
1, 2.
And 1, yes, 1, 2.
Okay.
And so since one is negative and one is positive, we know that there is a 0 somewhere between those 2 points. Now, it could be 1 or 0, couldn't it? Because it is inclusive. Okay.
So should we draw a dotted line in?
I did. Oh, it just did this. Okay, don't. This is just the same thing. I don't know why it came up differently. These are the directions. Look at those directions. They're kind of scary. Yes?
Yeah.
And that's why I put them there. It says use the intermittent value theorem and a graphing utility to approximate the zeros of the function. Okay, so we had this, yes. Ooh, I get thick lines.
Ooh.
Thanks. Had this, yes?
Yeah.
Okay, so then it says a graphing utility, so I pull out my what?
Calculator.
Graphing calculator, and you're going to put this in your graphing calculator,
I'm gonna put what in
the equation.
there? Okay, so y equals.
X cubed plus 2x. A lot of times, guys, these things are just to show you how to use the calculators to help you out. Plus 2x
Then we're gonna graph it.
minus 1. And you're going to hit zoom 6 because we messed with the window, yes? And we only need 0 to 1, don't we?
Yeah.
Okay, so I hit zoom 6. This is what you should get. You should get the parent function looking thing, don't you?
Mm-hmm.
Okay?
Mine's still loading.
You should get something that looks like this, yes?
Yeah.
Okay. I think maybe you hit it twice if it's still loading.
It must be.
Okay. Hit it
It's
again.
It's time.
Is it, wait. See this? You paused it. You were impatient.
Pause
The inner. You can see.
Whoa.
Okay, so we've got that. Everyone got that in their paper? Something like that? So we need to approximate this 0. So we need to zoom in. So you hit zoom, and there's number 2 is in, and it gives you a little cursor, and move it right to where you think the x-intercept is, and hit in. And did you get closer? Did you get closer? Zoom in.
Yes.
Okay. I still need to zoom in some more, don't I? Or do you think you can get a
Do I
good
need
approximation? I don't know. It's up to you.
Mm.
I want to zoom in again. So I'm going to hit zoom. And I'm going to hit in. And I'm going to move my cursor to where I think it is. And I'm going to hit in.
I can't even see any lines now. How do I unzoom?
Well, it
Hit
gives
zoom standard and go start over.
it gives you the thing at the bottom. doesn't
So
it, with the
now, what do you guys think your estimate is?
answer? -1.
Negative what your x-intercept?
Oh, X.
X. We're looking
0.
for the x. We're looking for the x-intercept.
0.
Really? The x value right there should not be 0.
What are we looking at, Miss?
The
Girl?
x-intercept.
0.5.
What?
0.5.
I think I'm looking at the wrong thing right now.
I'm pretty
Hold
sure
on.
you are.
0.5 am I?
Okay, Maddie says 0.5. Shelby, what do you say?
I was looking at the wrong one too.
The x-intercept.
I'm looking at the wrong one. That's what happened.
So
Hold
get on the right one.
Let me do a little moving look.
It says 0.47.
Okay, I'm estimating 0.45. Riley, what are you estimating?
No, I'm estimating like 0.5,
0.5 or 0.6? Or 0.6? Anybody else want to throw something out there, see if it
No,
sticks?
G, it's
Okay.
for sure 0.47.
Ah,
Mine's not even zooming in anymore for me.
Hit zoom standard and go back and start over.
0.43.
What?
Yeah.
What?
Okay, how can we make sure what it is instead of guessing?
So I can enter our x's.
No, how do we do this on here? We use the calc button. Yes?
Second,
So-
calc, value.
Just a second. Before you start that, you better be able to see both sides of this, okay? So second calc, we're not looking for a value. We're looking for a what?
0.
A 0. And then you need to do left and right.
You have to enter every time.
Yep.
What's happening?
And it's we're using the calculator to do it for us. Second calc. Remember doing that?
0.45.
Second calc. Zeros.
Oh, wait.
Oh,
Left and
yeah.
right.
What did I do?
I get 0.45. I was right.
Silly me.
You probably already did that.
I zoomed it and had 0.5.
Oh, no. How do I get back to that?
I got 0.45. And some other numbers.
Yep.
But we're not getting.
0.453339.
I'm pretty sure that was 0.47 or whatever.
Oh, no, I don't think so.
That's because you got to guess. You
So-
have to do
I
the third
did.
step.
So we're
I'm
supposed
pretty sure
to
it's the-
we're supposed to go through and prove that there is one. Then we're supposed to mess with our calculators so we get to know our calculators better. Got it?
Yes.
So we just put our x is equal to 0.47.
0.45 is what the calculator told you.
But it would be x equals 0.45. Like that would be your.
Yes, you're gonna put an estimate. You're gonna put so you'll be approximately and all your guys' guesses, and then you're gonna put calc. So you knew the calculator did it. X int equals. And actually, that one should be approximately as well, huh? Since we're rounding. And if we use Maddie's method of rounding, that goes to 7 somehow.
No, when I was looking at it and I was like moving my thing, it was saying 0.47 right where it intersected.
Okay, so now we're going to use the intermittent value theorem again, and this is exact from your homework directions, okay?
Yay.
It says exercise 91 through 94. Verify that the intermittent value theorem applies to the indicated interval and find the value of C guaranteed by the theorem. So we need to make sure that this function is continuous at both. So we need to plug in f of 0 again. And f of 3. Yes?
So we're going to put this in our calculator?
No. We're going to write it on our paper.
Oh, yeah.
F of
I
0.
think, can we try this?
Yeah.
Oh, okay. Go for
Unless
it.
it's harder.
It's just a little bit different.
Oh, never mind. I know how to do the 1st
We'll
one.
try this step.
Actually, it's about the same.
That f of c equals 0 though.
I know, we have to we have to show that. Like, we have to do the theorem to show that this happens.
Boom, I have it.
Okay. Do we get 8 and negative 1?
Oh. Sorry.
Okay. So all we have to do on here, guys, it says use the intermittent value theorem to indicate over the indicated interval to find the value of C guaranteed by the theorem. Okay. So now what we write is since f of 0 is greater than 0, meaning it's what?
Positive.
Positive. And f of 3 is less than 0, meaning it is negative. Then there exists a value C where f of C equals what?
0.
0.
Wait,
Since one is positive and one is negative, does there have to be a 0 in between the two?
Yes.
Yes. A 0, an x-intercept, and a solution are all three the same things, are they not?
Can we graph it out and do what we did with the last
Sure,
one?
we can practice that.
Okay, can we do it on our own?
Yes, you can definitely do it on your own. Okay, but again, the intermittent value theorem said there is an f of c, a c such that f of c is 0, yes? Did it tell me where it was at?
No.
No. So this is where Maddie wants to pull out the calculator and do it on her own and figure it out.
So we're finding the zeros now.
Yes.
I guess there's just 1 0.
Or you could just factor it.
Oh.
But yes, you can use your calculator to practice.
Found it.
Oh, what?
I don't know.
Found it.
They're pretty good. I just factored and found it.
Really improved. Can't
I just factored and found it.
Oh, it's a parabola.
Hold on.
Yeah, because it's x squared.
Yeah.
Good job.
Wait.
Hold on, I'm still getting
Now I'm going to
there. And then,
second calc 0. Wait, which one are we looking for?
so there's gonna be 2.
Well, not between that interval, they're not.
Oh.
Oh,
Between 0 and 3. So we can go to window minimum.
0. You might get on to do -1
I got 2.
and 4. There's only 1 0 in that interval.
No, I got 2.
Oh,
That's my
okay.
0.
Yes.
My
Yes.
0 is 2.
Yeah, because I factored and found the 0 was 2 also.
Hold on, I'm still getting there. Okay.
Why'd you get 4?
Because I factored it. The factors of
So I
8
don't
that
need
add to
find
6.
4.
No, you don't. That's
So-
why I factored. Look, Maddie, I factored and found 2 and 4 and
Yeah.
circled what?
2.
2.
Okay, so I put approximately.
Nope, it's not approximate.
Oh. So calc x equals 2.
2. Because you used the calculator to find 2, didn't you?
Yeah. Are we done with our notes?
Mm-hmm.
Boom.
I'm pretty sure. Is everyone done writing what I wrote up there?
Shelby?
Because once I proceed, I can't go back anymore.
Let me write.
Oh.
I'm
Takes
good.
off her glasses.
I like.
She's getting serious. So it's, what did I say it was? Calc? Wait.
Ah. Nice. That's why nothing like
What?
skipped a bunch of stuff like a dummy.
Oh.
Be nice?
Like a dummy.
Like a
I'm pretty sure this is my last one, so I'm just going to stop it. I'll pause it. How about